All right, so in the last section, we had taken a look at the graphs of sine and cosine. We looked at the traditional method on how to graph or sketch out those curves, and we also had taken a look at how to graph on the calculator. Now, as far as the graphing is concerned, in the next section, when we look at the other four trig functions, we mainly graph the four remaining trig functions by using some type of technology. Okay, and you'll see why as we go through the function capsules. So in this instance, I guess before we begin, and I would not be thorough if I didn't actually go through this. If you're taking physics, or if you plan on taking physics, physics is a prerequisite for this course. And we had an instructor at one point in time. He's no longer here with us, and he was just adamant about the sine and cosine values and their ranges. So I'm going to kind of go through that just momentarily. This will be it's applicable in this class, but in a physics setting, this is something that should be like understood. Okay, I'm going to draw out a right triangle. All right, so this is A, this is B, and this is C. All right, and we have a leg, or I'm going to call this X, and I'm going to call this Y, and I'm going to call this R, right? So keep in mind that this thing is in an X and a Y coordinate system. Right, so we think about a right triangle. In a right triangle, the hypotenuse, which is opposite the right angle, right, that's always the largest side, okay, for any right triangle. All right, when we talk about the sine, so let's say the sine of some angle, right, the sine of some angle, that would be the y value over r, right? So here again, I'm kind of referring to the six trig functions as they relate to x, y, and r. Now, there's just one thing about the sine function. And I'm just going to put some numbers to these. So I'm going to call this x is going to be 3, y is going to be 4, and r is going to be 5. Okay. So this is what's called a Pythagorean triple, 3, 4, 5. So if I take 5 squared, right, that should equal to 4 squared plus 3 squared. All right, so we have a right triangle. Now, as far as the sine is concerned, if the denominator, which is r, is always longer than any other side, there's something that can be said about the sine. Right, so I'm going to write this out. So r is 5 and y is 4. So my sine would be 4/5. If the denominator is always larger than the numerator, so I'm just kind of write some numbers out. So let's just say I have 1 over 5, I have 2 over 5, I have 3 over 5, I have 4 over 5. Notice that if the denominator is always bigger than the denominator, the value of the number itself can never exceed a positive 1. Right? Because the only way you can exceed a 1 is if the numerator was bigger than the denominator. But in a right triangle setup, r is always the largest side. All right, so the sine value, I'm going to actually write this out over here. So the sine value is actually between -1 and positive 1. Right? So the sine value is trapped in between negative 1 and positive 1. It can never be okay, this is the way that should be written. All right, so the sine is in between negative 1 and positive 1. The same thing is true for the cosine, right? If you look at the cosine value is x over r. So if r is always the longest side, right, the same thing can be true for the cosine, right? It also has to be in between negative 1 and positive 1. Right, so the same thing is true as for my cosine. The cosine is less than or equal to negative 1, and it's greater than or equal to positive 1. Right. My tangent value, so notice that the tangent is y over x. So it doesn't matter if the numerator is bigger or the denominator is bigger. The tangent can take on any value. All right. If we look at the reciprocals, right, and that's what we see on the slides. I'm going to go back to our slides here. Oops. I'm sorry, and I do have my signs incorrect. This should be less than or equal to. Okay, I have to get into the trig mindset. Okay, so the cosine and the sine, you write that out a little bit better. Okay, they're both between negative 1 and positive 1. All right, so if we take a look at, okay, this capsule, it says that if the sine is equal to 1, the value of the cosine is equal to 1. If the sine is equal to negative 1, then the cosecant is equal to negative 1. So, excuse me, that's the sine is equal to 1, and the cosecant, which is the reciprocal of the sine, is 1. And similarly, if the sine of x is equal to negative 1, then the cosecant of x is equal to negative 1, right? We have that the sine that should be less than or equal to 1, and it should be greater than 0. Okay, they kind of got this written in a they're not actually writing this out as a compound interval with negative 1 and positive 1. And in the secant, the cosecant, it should be less than negative 1, or it should be greater than positive 1. Right. So we'll take a look at the graphs. So notice here we have two curves. We have, I'm going to blow this up. On the left, we have the cosecant curve. And keep in mind that the sine is the reciprocal of the cosecant and vice versa. The cosecant is the reciprocal of the sine. So notice we see that the red curve is the sine curve, right? And it runs between negative 1 and positive 1. We have the blue curve, which is the cosecant curve, and it is greater than positive 1, and it's less than negative 1, right? So the red curve is our sine curve. The blue curve is our cosecant curve. And we take a look at the second diagram. We have the cosecant, right, which is this red dash curve. And we have the reciprocal of the cosine, which is the secant, right? So the secant curve is the blue curve. All right, I'm gonna pull out the calculator and I'm gonna graph these two curves on using the calculator. All right, so I'm gonna clear out my home screen. I want to make sure that I am in rating mode. I'm going to clear out these functions. Okay, and I'm going to graph the cosecant, right? So keep in mind that I don't actually have a cosecant function on my calculator, but for my reciprocal functions, we can enter in the cosecant as 1 divided by the sine. So I'm going to graph the cosecant in my calculator as 1 divided by the sine of x. I'm going to hit zoom 6, right? So just keep in mind zoom 6 puts this in a -10 to +10 in increments of 1. And now I'm going to hit zoom and 7. And I want to just explain a couple of things about the graph itself. Now, as far as these vertical lines are concerned, these vertical lines are not actually a part of the graph. This calculator is in what's called connect the dot mode. And so it's going to take this point way up here and it's going to connect it with the point way down here. I believe if you have a TI-84 or higher, you don't actually see these vertical lines. I can actually take these vertical lines out if I go to y equals. If I scroll to the far left, I'm going to hit enter once. I'm going to hit enter twice, 3 times, 4 times, 5 times, and 6 times. And notice I get these dots, right? So now if I regraph, I don't actually see those vertical lines in my calculator. Okay, so that's the very first thing. Since I'm using a TI-83, right, I do have the vertical lines, but I want you to know that those vertical lines are not actually a part of your graph. Right, so you can choose to take them out, okay, by going into y equals, right, and I can change the line that's drawn. I believe another way you can take the lines out is in the mode section, and if I go into mode, it's in the connected mode. So if I change it to dot mode, and if I regraph using dot mode, notice that the vertical lines are now gone. The period for the cosecant curve is also 2 pi. We can graph the secant function. So I'm going to go back to y equals. So we don't actually have a secant function in the calculator, but we could graph it as 1 divided by the cosine. So I'm going to put in 1 divided by the cosine of x. And now if I graph, okay, notice I have the secant curve. Okay, so just notice that the secant curve, it sort of touches the y-axis. And if you look at the cosecant curve, notice that the cosecant curve kind of strays from the y-axis. Okay. Here again, the period for the cosecant curve is 2 pi. Right? And we'll talk more about the periods in a second. All right, so here's the function capsule for the cosecant and the secant function. First, it says that the cosecant function is discontinuous. So discontinuous means that, and I don't know what happened to my calculator. Okay, it's over here. All right, discontinuous means that, and both of the graphs are discontinuous. From algebra, If you have a continuous graph, that means that you can put your pencil on the paper and trace the entire graph without removing your pencil from the paper, right? However, for the secant and cosecant functions, in order to graph the entire curve, right, we can start tracing the curve, and then it comes to a point where we have to take the pencil off the paper, put it back on, and then continue to draw the curve, right? So that's a discontinuous function. The cosecant is discontinuous for all values for x that are equal to n times pi. All right, so if you take n, and n would be an integer, right, a negative or positive whole number, multiply that by pi, that will give you the points where your graph is discontinuous. There are no x-intercepts. Remember from algebra, an x-intercept is where your graph crosses or touches the x-axis, right? So notice that the cosecant as well as the secant curve, they have no x-intercepts. The period for both of these curves are 2 pi. The cosecant is an odd function. So remember that odd functions are symmetric with respect to both the x and y axis. The secant is an even function. So the secant is symmetric with respect only to the y-axis. All right, now let's practice graphing some functions. Okay, so we want to graph y is equal to 2 times the secant of 1/2 x. Okay, now as far as the graphs of secant and cosecant are concerned, we're going to graph secant, cosecant, tangent, and cotangent. We're going to graph on the calculator, and then we're going to match the calculator to the given answer choices. All right, so on the slides, we're just going through the process of how you enter these functions into the calculator. All right. All right, so we're asked to graph y is equal to 2 times the secant of 1/2 x. Right, so we're going to put this in the calculator. We have 2. I'm going to rewrite the secant of 1/2 x as 1 divided by the cosine of 1/2 x. All right, so I've simply rewritten secant as 1 divided by the cosine. And now I'm going to recombine this to make one fraction, right? So whenever we multiply a whole number times a fraction, we can multiply the whole number times the numerator only. Okay, and this is what we're going to put into the calculator. All right, so I'm going to turn my calculator back on. I'm going to go to y equals. I'm going to put in 2 divided by the cosine of 1/2 x. Right, so there's a couple of different ways I can write out 1/2 x. I can write it out as 0.5 x, right, because 0.5 is 1/2. I can also write it out as x divided by 2, right, because here again I can multiply x, which is a whole number, times the numerator only, right, and I can divide that by 2. So I'm going to leave this written as 2 divided by the cosine of x over 2. And now I'm simply going to hit graph. All right, and thus we have the graph of 2 times secant of 1/2 x. All right, next we're going to graph 1/3 times the cosecant of x minus pi. So y is equal to 1/3 times cosecant of x minus pi. So I have 1/3, and I'm going to rewrite the cosecant as 1 divided by the sine. So I'm going to now make one single fraction. So I'm going to multiply the numerators and multiply the denominators. So I have 1 divided by 3 times the sine of x minus pi. And here is where you have to be careful when you're putting these functions into the calculator. So I'm going to go back to y equals. And I'm going to clear out this function. I'm going to put in 1 divided by, and I want to make sure that I use a set of parentheses about my denominator. And I'll show you why in just a second. So I'm using a begin parenthesis, 3 times the sine, and notice I'm giving another begin parenthesis. I'm going to put in the argument for my sine function, so that's x minus pi. I'm going to close off the argument for sine. I'm going to close off my denominator. And now I'm going to graph. Right, so keep in mind these vertical lines are not actually supposed to be here. So let me just put this. It's supposed to be in dot mode. All right, so this is the graph of 1/3 times the cosecant of x minus pi. Now here is why the parentheses in the denominator are important. If you did not include that extra set of parentheses in the denominator, then your calculator is not performing the order operations, right? Which is, if you're dealing with a fraction, you should simplify the top, you should simplify the bottom, and you should divide last. Okay. If you were to graph without using a set of parentheses, here's what's going to happen. Right, we actually would be graphing a sine curve. Right, because what your calculator is doing is it's performing the order operations, but it's doing it in a not correct fashion. It's actually dividing 1 and 3, and then it's evaluating the sine. Okay, so without a set of parentheses in the denominator, all right, you won't get the right graph because your calculator is not performing the order operations. All right. So with that extra set of parentheses in the denominator, notice that we now have the cosecant function. All right, so now we're going to look at the graphs of tangent and cotangent. Okay, so the only two continuous graphs are sine and cosine, right? You can put your pencil on the graph and actually trace those graphs without removing the pencil from the paper. However, the other 4 remaining graphs are all discontinuous, and those graphs are graphed by using some type technology. So now let's take a look at the tangent function. Now for the tangent and the cotangent, there is a change in the formula for the period. For the tangent and the cotangent, right? The period is something a little bit different. So for cosine, sine, secant, and cosecant, the period formula is 2 pi divided by b. However, if you're dealing with the tangent and the cotangent, the period is pi over b. Right? So remember, the period is just the amount it takes to make one complete cycle or revolution. Okay, so we have a new formula for the period of the tangent and the cotangent function. All right, so it says that the period is pi, so it makes one complete revolution in pi radians or 180 degrees. And it has no amplitude, right? If we take a look at the graph itself for tangent, you read any graph just as you read sentences from left to right. And as we read this graph from left to right, notice that the graph is strictly increasing. And it's increasing without bound, right? These arrowheads let you know that this thing keeps going up. And then this down arrowhead lets you know that it keeps going down, right? So there is no amplitude or maximum height. Its values are 0 when the sine values are 0, and it's undefined when the cosine value is 0. Okay, so just keep in mind an undefined value is when you have 0 in the denominator. Right? It says as x goes from negative pi over 2 to positive pi over 2, the tangent goes from negative infinity to positive infinity. Right? So it goes from, as we read the graph from left to right, just notice that it goes from negative infinity to positive infinity. And we're also given that the x-intercepts are in the form of n times pi. Right? So keep in mind the x-intercepts are where your graph cross or touch the x-axis. Right? So really quick, I'm going to graph this in the calculator. So I'm going to just clear out the y sub 1 function, and I'm going to enter in the tangent of x. Okay, and I'm going to graph this using the dot mode. Right, so if we hit graph, notice as we read the graph from left to right, the graph increases. Okay, so a tangent function should always increase from left to right. Now we'll take a look at the cotangent function. Okay, and if we read the cotangent function from left to right, notice that the graph descends or goes down. Here again, the period is still pi. The values are 0 when the cosine values are 0 and undefined when the sine values are 0. The x-intercepts are in the form of 2n plus 1 times pi over 2. Okay, now the x-intercepts aren't important for this course. We won't actually, be asked to find those things, but here are the formulas. All right, so let's take a look at how we would graph. So in this case, we're asked to graph y is equal to 1/2 times the cotangent of 2x. All right, so we're going to graph y is equal to 1/2 the cotangent of 2x. So we don't have a cotangent function in the calculator, but we can write the cotangent as 1 divided by the tangent of 2x. And now I'm going to write this out as one fraction, so I'm going to multiply the numerators and multiply the denominators. So I have 1 divided by 2 times the tangent of 2x. I'm going to add a set of parentheses about the denominator, and then we're going to graph. All right, so if I hit y equals, I'm going to clear that out. So I have 1 divided by, and I'm going to use a set of parentheses, 2 times the tangent of 2x. I'm going to close off the argument for tangent. I'm going to close off the denominator, and we're going to graph. Okay, and I'm just going to take those lines out. All right, and we have our graph. All right, so before we move any further, I want to talk about, there's something called the negative number identities, and they are not actually on the formula sheets. Okay, I'm just going to write these out. And they're called negative number identities. Right? And here they are. The cosine of negative x is equal to the cosine of x. Now, for some of the problems that we're going to deal with in the directions, they may ask you to write each angle as a positive angle, right? So here we have the negative number identities, right? So the first one says that the cosine of negative x is equal to the cosine of x. Next, we have the sine of negative x is equal to negative times the sine of x. So if you look closely in this example, we have the sine of some negative angle, right? The sine of negative x. And that should equal to a negative times the sine of the positive angle. And then we have tangent, right? The tangent of negative x is equal to negative times the tangent of x. And then we have our reciprocals, right? So the reciprocals follow. The reciprocal of cosine is secant. The reciprocal of sine is cosecant. And then the opposite of tangent is cotangent. All right, so we're going to take a look at these by using a calculator just to verify that these things are true. All right, so I have our calculator, and I'm going to go into the mode section, and I'm going to just change this to degree mode, right? Just because we're going to use just degree measures. So let's just kind of verify this first identity. It says that the cosecant of a negative angle, so I'm just going to use 30. So the cosine of negative 30 degrees is 0.866. So from what this formula is saying is that the cosine of negative 30 degrees should equal to the cosine of positive 30 degrees. Right? So I can change my negative cosine angle to a positive cosine angle, and they have the exact same value. Okay. So I'm alluding to this because in some problems it may ask you to write everything as a positive angle. So if, let's say, if your final answer is the cosine of negative 30 and you put that in and they mark it wrong, you are supposed to use a negative number identity and simply replace negative 30 with positive 30. Because you're not changing the value of your trig expression, you're just changing the angle from a negative to a positive. Okay, let's look at the sine. It says that the sine of a negative angle, so I'm going to use negative 30, right? That gives me negative 0.5. That should equal to a negative times the sine of positive 30. Right, so notice we've changed our angle from a negative angle to a positive angle, but the value is still the same. And then lastly, we have the tangent of negative x is equal to negative times the tangent of x. So I'm going to use the tangent of negative 30, and I get negative 0.57. That should equal to a negative times the tangent of positive 30. Right, and notice I get the same value. The same is true for our reciprocals, right? The secant of negative x, that's equal to the secant of positive x. The cosecant of negative x is equal to negative times the cosecant of positive x. And the cotangent of negative x is equal to a negative times the cotangent of a positive x. Right, so using the negative number identities, we can express a negative angle as a positive angle. All right, so if we take a look at some of the problems that are in X, Y, Z, for the first graph, for the first problem, you're just asked to match graphs. All right, so we talked about the tangent, and as you read the tangent, right, from left to right, it goes up. So I believe this first graph would be a tangent curve. All right, and you can actually verify that by graphing on your calculator. All right, so if I were to put in the tangent of x, okay, and here again, you want to make sure whenever you graph that you are in radian mode. Okay, so that's the reason for the graph that looks the way it looked, okay, because I was not in radian mode. Whenever you graph, you should always be in radian mode unless the problem states otherwise. All right, so we can match up A as the tangent curve. If we look at B, I believe that would be the cotangent curve. So I believe B would be the cotangent curve. We can graph the secant. Okay, remember the secant is 1 divided by the cosine. Right, so just remember that the secant curve, the basic secant curve, it actually hits the y-axis. Right, so graph C would be a secant curve, right, because it actually hits the y-axis. All right, and then by elimination, D would be our cosecant curve. All right, so remember you can graph the cosecant as 1 divided by the sine. Right, and when you graph, notice that the curve, it doesn't actually hit the y-axis. Okay, so that would be D. All right. On some problems, you're asked to, oh, I guess I should check it. On some of the problems, you're asked to match a graph. Where are they? Here they are. You're asked to match, okay, a graph to the given answer choices. All right, so let's take a look at problem number 12. We're given 2 times the secant of pi times x plus 1. Okay, now as we match our calculator to the given answer choices, there's just a couple of things you want to keep in mind of. First off, notice that both the x and the y-axis are in increments of 1, 2, 3, 4. So when we graph, we have a choice to graph standard, and right, by graphing standard, that's the -10 by +10 increments of 1. We can also use the trig scale, which gives us 0, pi over 2, pi 3, pi over 2, and 2 pi. Right? Since our x and y axes are numbered, 1 through 3, we're going to use the zoom standard when we graph. Okay. Also, when you're matching your calculator choice to the given answer choices, we want to concentrate on the origin. Okay, we want to concentrate on what's happening both on this y-axis and on the x-axis. All right, so I'm going to go to OneNote. All right, and we're going to just write out the function that we're going to put in the calculator to graph. All right, so we have y is equal to 2 times the secant of pi x plus 1. So as we did earlier, I'm just going to rewrite the secant as 1 divided by the cosine. Next, I'm going to combine everything to make one fraction. So I'm going to multiply 2 times the numerator. So we have 2 divided by the cosine of pi x plus 1. However, I'm going to include an extra set of parentheses about the denominator. So now I'm going to go back to y equals, and I'm going to put in the function 2 divided by, and I'm going to use a begin set of parentheses, the cosine of pi times x plus 1. I'm going to close off the argument for cosine, and I'm going to close off the denominator. Since my scale was going from +3 to -3, I'm simply going to hit zoom and standard. All right. So from this point, I'm going to do a couple things. First off, I'm going to take those vertical lines out of the calculator. So I want to go into mode. And I'm just going to reset this to a dot mode. The next thing I'm going to do is I'm going to rescale my axes. So notice for my x-axis, I'm going from -3 to +3 in increments of 1. So in order to change the scale on our calculator, I'm going to hit Window. I'm going to change x minimum to -3. I want to change x max to +3. My x scale is still 1. And if we take a look at our y-axis runs from -5 to +5 in increments of 1. You always want to leave this x res or x resolution on 1. So now I'm going to hit graph, right? And we have our graph. All right, so matching up the answer choices, I'm going to pay careful attention to the origin. Right? So it looks like on the y-axis, right, the upper part of our y-axis, there is a portion of our graph that actually touches the y-axis. Right, so I'm going to kind of look for that in the answer choices. So it looks like D would be our correct answer choice. All right, so once again, you want to make sure that you write out your function appropriately. Once you graph, you can go in and change the dimensions on your calculator. And when I say dimensions, I mean the x minimum, x max, x scale, y minimum, y max, and y scale. All right, but always leave your x resolution at 1. All right. Let's see, there were some other problems. Okay. For example, problem number 2, right? You're asking for period and the horizontal shift. Right, for this problem, we're given 3 times the tangent of 3x divided, 3x minus 18. We have to find the period and the horizontal shift. 3 tangent 3x minus 18. All right, so I want to write that out. So this is y is equal to 3 tangent 3x minus 18. So we want to find the period and also the horizontal shift, which is the phase shift. Okay, so remember we're dealing with a tangent function, and a tangent function has a period of pi divided by b. Right, and remember that b is the coefficient of x. So if we look at our equation, notice that the coefficient of x is 3. So our period is pi over 3. We're also asked to find the horizontal or phase shift. So that horizontal phase shift that's going to equal to negative c over b. Right, so remember from our model form we have a, b, c, and d. Right, so if I actually had to add a d, it would be plus 0, right, because there is no shift up or down. So in order to find the phase shift, it's going to be negative times c, which is negative 18 over 3. So we have a negative times a negative 6, which is positive 6. All right, so we have a period of pi over 3 and a phase shift of positive 6. All right, so just keep in mind that the tangent and the cotangent, they have a different function for the period than the other 4 trig functions. Okay, we're also given problems such as these. Okay, I think that's okay. And we're given problems such as these. It says if the secant of x is equal to negative 5.5, then we're asked to find the secant of negative x. All right, so if we go back to our negative number identities, right, the secant of negative x is equal to the secant of negative x is equal to the secant of positive x. So the secant of negative x, I believe it would be negative 5.5. All right, so that's kind of using those negative number identities. All right. Now there are some questions that ask about vertical stretches. Let's see, I believe they were a little bit further down. Okay, yeah, there are some problems that ask about this vertical stretch. I think it just may be that only that one problem. Or a stretching factor. Yeah, there's others that ask about a stretching factor. All right, so stretching factor or vertical stretch factor. Let me kind of explain that for a second. That stretch factor, right? That's basically going to be the amplitude. When we talk about, I'm going to relate this to an algebraic function. So I'm going to graph x squared. And if I were to graph x squared, okay, let me do zoom 6. Right, if I were to graph x squared, this would be the graph of x squared. For y sub 2, I'm going to graph 2x squared. And I'm going to use connected lines again. So if I were to graph 2x squared, notice that 2x squared is actually a vertical stretch. So if you think about a vertical stretch, if I were to take the two ends, let's say of this basic x squared graph, and if I were to vertically pull up on those ends, right, my graph should kind of close in on itself. That's considered to be a vertical stretch. Right? So let's see what happens if I put in larger coefficients. So let's put in a 3. So if I put in, well, let's use 4. I'm going to put in 4x squared. And if I graph 4x squared, right, notice that my graph is vertically stretched even further. Right, so it seems like the larger number I put in, the more stretch I get. So example, let's say if I go in and if I put in, let's say 100x squared, right? Notice that I'm almost on the x-axis, on the y-axis, excuse me. So let's say what happens if we put in a number that's less than 1, greater than 0, but less than 1. So I'm going to kind of clear these functions out. So I'm going to put in 1/2 or 0.5 x squared, and let's analyze the graph. All right, so we have the x squared graph, and here we have a graph that looks like it's not really stretched. This would be called a vertical shrink. Right, so notice I'm using a number between 0 and 1. So if I could physically describe a vertical shrink, if we were to grab the two ends of our x squared graph, and instead of pulling up, if we were to push down, right, that would kind of flatten out our graph. So let's see, I'm going to put in, let's say 0.1 x squared. I'll put in an even smaller number, and let's analyze the graph to see what happens. So notice that the graph shrinks even further, right? Or it's kind of flattening out more. Right? So let's say if I go in and let's say I put in 0.0001 x squared, right? I'm going to put in an even smaller number. Well, that may be too small. I think it's actually laying on the x-axis. Let me take some of the zeros away. I'll put in 0.01 x squared. So that's the first one, the second one, the third one, and the fourth one. Okay. So notice as we get closer and closer and closer to 0, the graph actually shrinks down or flattens towards the x-axis. So when you're looking at problems such as these, it says the vertical stretch factor, I believe that would be 3. And for the period, right, remember the period for the tangent function is pi over b, right? So in this case, b is 2. So we would have our period is pi divided by 2. The vertical stretching factor should be 3. I think I put in a 0.3, but that vertical stretch factor should be 3. All right. All right. So are there any questions about what we went through today? I'm going to actually stop the recording.